And this is just, I printed out a page from the syllabus that is on the web. And so we're going to talk about the Canvas modules that cover what's going to be on exam 2. Starting off with continuity, divergence, and vertical motion, and we end with cyclogenesis. Chapter 5, I believe it was. It does not include the material that is on waves. So, continuity, divergence, and vertical motion. You've had basically a lot of this in previous classes, but we want to review it a little bit. And we had an equation of mass continuity, and it had a density in here. Once again, you don't have to memorize equations, but if I give you an equation, you need to know what it's all about. And in some of them that I will point out later, you would need to give each term a name. Now this one is not that way, but if I would put it down, if I would write the equation down, you would say this is the equation of mass continuity. And then we use the chain rule to break up the partials, and we make what is called the Boussinesq approximation, which is commonly referred to as equation of continuity for an incompressible fluid. That's the equation that we spent quite a bit of time looking at, because it was real easy for us then to determine the sign and sort of a magnitude of vertical motion given a profile of horizontal divergence. Now, we said that while this is a nice simplification, because we end up with partial U, partial B, partial W, so forth, equal to 0, when we make this approximation, we're holding density constant. That's the definition of it. And if we're holding density constant, we can't have pressure changes. So we are giving up a very important thing in order to make it easy to work with. Because, obviously we want to know if we're going to have pressure falls or pressure rises. And that equation does not give it to us. So, we can think of it as a box that is sealed, and if we squeeze it horizontally, using horizontal convergence, it's going to stretch out vertically. So that's the way that we can link horizontal motions to vertical motions. Now, one important thing that we talk about here is what is the level of non-divergence. So you certainly need to know what that is. And in a well-defined system, whether it be a high or a low, not just a piddly thing, but some kind of well-defined system, it's usually around 600 millibars, which we approximate as 500 millibars. So then we got into these various examples of if you have a profile of horizontal divergence, if that is a given, then we can superimpose the vertical motion profile. And it is the process of integration which relates things to area. So this was on one of the preceding pages. Vertical motion at level L is equal to negative of the integral from surface to L of horizontal divergence integrated over C. So that's an equation you need to know and be able to use, like we did here. So in your case, I would give you the solid line, which was the profile of divergence, and you would have to be able to superimpose the dashed line, which is the vertical profile of vertical motion. And remember, it's all area, and you're always looking below the level that you're at.
Can you redefine the level of non-divergence? I can't seem to find it in the...
It's just a level where you have zero divergence. You don't have any divergence, you don't have any convergence. So if we look at any of these graphs here, like here is a level of non-divergence. We go from convergence near the surface, divergence aloft. So separating the two, you have an LND. Here's another example. Here we had some, and here we had some. So it's simply where divergence equals zero. You don't have any positive, you don't have any negative. Any questions about how to do this? Yes?
It's not about how to do this, I was just wondering, would the practical kinematics and the kinematics 2 sheet be on the exam, or are we just starting with this material and moving forward with that?
Practical kinematics.
It's the one with like the curvature and the shear and.
Oh, that was covered on the previous exam.
So, okay.
Yeah, so that's not on this exam. Mhm.
For the last diagram, why do you have the dotted line or the dashed line for the W going like after you finish shading in the area? Like at the top?
This one?
Yeah.
Well, by the different kinds of shading and hatching, I was trying to show you what kind of areas cancel each other out. So starting off at the bottom here, we have convergence closest to the surface. So that right away rings the bell. If I have convergence near the surface, I've got to have rising motion near the surface. So that gets you off to a start. And we're always thinking areas. So I'm working my way up. And when I get here, that's a level of non-divergence, one of them here. And up above that, we have horizontal divergence. So now I'm starting to subtract out some of the convergence that I had accumulated below. You know, once again, we're always looking below the level that we're at, and asking ourselves, what is the net effect? Do I have net divergence or net convergence? So, when I get to this level, what the shading was trying to show is that this area now is equal to this area. So that means the vertical motion goes to zero here. Notice where the max is. The max upward motion was where the LND was. So those are the kinds of things I'm going to be looking for. Do you have a max or a min at the LND?
Right. But then when it, like at the top, very top of the diagram, like the shading stops, but the line keeps going.
Yeah, well, this is upper level convergence, so just to keep on going here, at this level, the two cancel out, so now I have upper level divergence. I'm working my way up, so I have descent, and here's another LND. So now I have this area of descent, and then I move upward, and I start canceling out again. And so, in my estimation, this area up here was equal to this area down here. Now they have very different shapes, but my guess was this area equals this area, and that's when the vertical motion went to zero again.
Okay, so like the net motion, because the dashed line keeps going after that, is technically like rising?
Yeah.
Okay.
Because I have this upper level, see, once I get above this altitude, now I still have some leftover convergence at the very top. And so that's going to mean rising air. Once again, the big rule is, at whatever level you are, start at the surface, work your way up, always look below. What is the net effect below? Convergence or divergence? And that will determine whether you have rising motion or whether you have sinking motion.
Is there always a peak whenever you're at an LMD for the ascent
Yes.
profile?
It's either a peak or a zero. In this one, it was a peak here, and here was another one. Well, this one's a little more complicated, but yeah.
Was that just because the areas cancel out, so that's why you put it?
And I had some leftover. Yeah. But I was trying to show by the shading here what areas I thought canceled each other out. So if you haven't looked at these things, you need to spend some time and go through them and make sure you understand them. Mhm.
Will you, like, examples on the test be, like, unambiguous, like, with the areas and stuff? Like, will it be clear, like, where the areas cancel out?
But you get some leeway.
Okay.
You know, I had to eyeball this too, in all of these. And I definitely give you some leeway, because what you see or what you interpret may be a tad different from what I interpret. But I have to be able to tell that you understand what is going on about areas canceling and all that stuff. But, no, I'll give you a little leeway.
So that graph has 3 LNDs then, where W equals 0 is
One.
also LND?
Here's the first one.
Right.
We don't count the surface. So here is number 1, and the next one here is number 2, and at the very top would be number 3.
Okay, cool.
When you said you wanted us to be able to super, put the dashed lines on there too?
Well, yeah, the dashed line is the vertical motion line. So that's what we're trying to get at all of this. We're trying to get a feel for whether we have ascent or descent based on the profile of divergence.
And just to reconfirm, for this one, you guesstimate if we were at the very, very top of your drawing, then it would be the one slightly above it. That would be net ascent.
Well, the way I have the solid line drawn here is that you have ascent. Is that what you're talking about?
Well, I was talking about, so vertical motion, sorry.
Yeah,
Yeah, so
it's
there's,
ascent
yeah.
here.
Well, I'm saying for the whole column, it adds up to ascent, right?
It adds up.
Yeah.
Well, yeah, okay. Sir.
Keep in mind that in the end, the atmosphere is not going to lose mass in the column. That's
No.
kind of what you're thinking about.
Nope.
Okay, then we got into thermodynamic diagrams. Most of this I think you should know already, so I'm not too likely to ask you about it. But I think you know the layout of a SQT log P diagram. But if you don't, good idea to check it. Now, we did define some special lapse rates. Yes?
So for this, you're not gonna be being like, oh, explain what the mixing ratio is.
Well, we hadn't come to that, but the answer is yes, I will expect you to know that. That's on some upcoming pages.
Oh, sorry.
So, you need to know or sketch what standard types of lapse rates are. So what do we mean by an adiabatic layer? Well, you need to know. Well, for adiabatic lapse rate. What do we mean by an inversion? Well, we have a negative lapse rate. And the reason we have a negative lapse rate is when we define lapse rate, it has that preceding negative sign. So the lapse in lapse rate just assumes temperature is decreasing with height. So, Then we come into these, this is a more clear-cut example. These are our standard types of inversions. So you need to know what they look like and be able to sketch them. So we had subsidence, which we also saw in the vicinity of a dry line, and it really wasn't subsidence there. It was air coming from different locations. So, but we still call it a subsidence inversion. That's the standard name. Frontal inversion, it has a different shape. So here, the dew point profile parallels the temperature profile. Wasn't the case, but there's subsidence inversion. Then we had a surface radiation inversion, very common early in the mornings, and finally the tropoplasm. Yeah, this is what you were talking about. Now, yeah, you ought to know these terms. You've had them before, and I just assumed that you know them. And so I could definitely ask you what they mean. These are all fair game.
I think she might have been asking because you said you wouldn't ask about the diagrams. So do you mean like interpreting the actual diagrams? Like you want us to know the terms but not how to find them on the graph?
I'm not going to ask you to sketch the lines on the skew T.
Okay.
Okay, the adiabats are oriented this way and the isotones are oriented that way. But I could ask you, say, sketch a frontal inversion,
Okay.
temperature, dew point, things like that. What do we mean by an adiabatic layer, or you know, that kind of stuff.
Okay.
So these are all terms, you've had them before, but just because you've had them before doesn't mean you can forget them. So you need to know them. I guess the one that we use the most in the upcoming pages is equivalent potential temperature, theta E. So what is it? Well, we have a definition for it somewhere. Lost it, but anyway. We know how to do it on the SKU-T, but what does it mean? It means that I'm going to take a parcel and I'm going to lift it until it's saturated. I am lifting it to its LCF. And then I keep on lifting it, but because I'm saturated, I go up to saturated adiabat, and I do it until all the moisture is condensed out, bring it back down to the surface. Well, bring it back down to 1,000 millibars. So all the latent heat that was hidden within the water vapor has now been used to heat the parcel. So theta E is going to be greater than Plano potential temperature. Unless the air were totally dry, which never happens. So, on these SKU-T procedures, for example, with theta E, well, first we need to get saturation. So we go up the dry adiabat from the temperature, we go up the mixing ratio from the dew point until they intersect. Why do you do it that way? Why don't you do it any old way? Okay, questions like that. Then, once you reach the LCL, why do you go up to saturated adiabat? Why don't you keep on going up the dry adiabat? So, we need to have a reason for what the procedures call for at this stage in your careers. Okay, some pictures. This page evidently got out of order, but it was, you know, the definitions for what we saw on this page. So we had some various kinds of inversions and lapse rates. So here we have some mathematical definitions. Here's equivalent potential temperature. So this tells what you do, but I expect you to know more than what you do. You need to know why it would be done. Or when you look at a SKUT on the web, you need to know, oh, they need, yeah, I know what that is, and if I had to, I would know how to do it, and I would know why you have to do it that way. Question?
No.
Precipitable water, well, what is it? So here we were talking about finding the LCL. Well, I got ahead of myself. Then we have example. We talked about positive areas, negative areas on the SKUT. If you have the right kind of SKUT, area is proportional to energy. So a certain positive area corresponds to a certain value of joules per kilogram. Same thing with negative. So we had a few new terms. Level of free convection. What is that? Is anything in this world really free these days? Well, convection sometimes can be. Yeah.
It's for the level where a parcel can start rating with being by itself.
By itself, right. No more forcing is required. No more pushing upward. It's now void. Negative area, that means you got, somehow some energy has to be added because the parcel doesn't want to go up on its own. It has to be somehow pushed. You know, mechanical lifting up and over a mountain or rising in a low or something like that. But once, if we could push it, if the atmosphere could push it to its LFC, then it would be positively buoyant and it would accelerate further on its own. We can also have parcels rising because they were heated enough. Usually by the sun heating the surface then heats the air above it. So that got us into the world of the convective condensation level. The height to which a parcel of air, if heated sufficiently from below, will rise adiabatically until it is just saturated. And from a practical point of view, it is usually the height of the base of cumuliform clouds, if heating is the only mechanism. So we've all seen situations where this would be a summertime thing, starts off clear. And all of a sudden, as the day progresses and it warms up, we see some little cumulus clouds developing. What happened? Convective temperature was reached. And air at the surface was able to reach its convective condensation level. So, now we're talking about ascent due to heating. We have a parcel that was heated enough it became buoyant and rose to saturation. Previously, we're talking about a parcel rising because of some kind of mechanical process that I described earlier. So the LCL and the CCL both talk about, well, now I'm buoyant, but they're approaching buoyancy from two different ways. One is heating, the other one is force lifting. And if we would compute the CCL on a SKU-T and compute the LCL on a SKU-T or the LFC on a SKU-T, they would not be the same, because they're two entirely different things. So once again, why do you do it this way? Why do you start off at the dew point and keep on going until, well, start at the dew point, go up the mixing ratio line until it intersects the sounder? That is the CCL. And then if you bring down the dry adiabat, you get convective temperature. So think about that for just a minute. If I heat this surface air, right now it has this temperature. But let's say during the course of the day it warms up to this temperature. Then it's as though I'm calculating an LCL, but I'm not. At intersection, that's your CCL. But once again, you're rising up a dry adiabat and you're rising up a saturation mixing ratio line. Now, question, why do you follow the dry adiabat when you lift and you're unsaturated?
Because it does not, there's no moisture to release latent heat.
Okay.
Condensing, so you're going to dry out, ideally, around that 9.8.
Okay, that's all good. Let's hone in on a little bit more. If we have an unsaturated parcel and that rises, it's going to cool at the dry adiabatic lapse rate. And that's what the theta lines are. All of those theta lines have a slope of 9.8 degrees Celsius for every kilometer. Or another way you could say it is that if we have an unsaturated parcel like we do here, or if we're finding an LCL, is that every dry adiabat can be labeled as a value of potential temperature. You remember that from thermal class? Every dry adiabat crosses 1,000 millibars at some value, and so every dry adiabat could be labeled with a temperature that would be its potential temperature. Does that bring back happy memories from semesters gone by? So, a parcel conserves its potential temperature during this lifting if it's unsaturated. And a dry adiabat is a line of constant potential temperature, so you go up that line. Or you say, the alternative way of saying it is that, well, if it's not saturated, it's cooling at the dry rate, the dry adiabatic lapse rate. Yes, sir?
I had two questions. So would it be fair to prepare for a SKU-T question where you ask us to find numerically different values of like theta E?
I'm not going to give you a SKU-T and ask you to calculate anything from it.
Okay. And secondly, so potential temperature is only conserved for dry adiabatic, but if it's moist, then all bets are off. But theta E is conserved no matter what.
Yes.
regardless of saturation.
Yes, that's true. And, if a parcel is saturated on a SQT, it says though further lifting goes along the saturated adiabatic. Cause that's the saturated adiabatic lapse rate, moist adiabatic lapse rate. Or you could call it a pseudo-adiabatic lapse rate, whichever. And the moist adiabatic lapse rate is not a constant. The dry rate is, the moist rate is not. And there's a simple reason for that. That as air gets cooler, its capacity to hold water vapor gets smaller.
Which means less of it can.
Less, and if you lift it, less water vapor to condense and release its latent heat.
And that's why it becomes parallel with the dry adiabats.
Yeah,
at a certain-
so what does it mean when the moist adiabat becomes parallel to the dry adiabat?
That means they're drying at the same rate. Or that means you're conserving your potential temperature at that point.
True, but let's poke at it a little more.
Condensed out all your moisture. Means you condensed out all of your moisture. So
Right.
the parcel's dry.
No more moisture to be condensed, no more heat to be released, latent heat to be released, and the dry rate equals saturated rate. Therefore they're parallel. Yeah. So here's the CCL diagram. So we talked about positive areas, we talked about negative areas, and we said that area on a SQT is related to energy. So if it's related to energy, we can quantify it. So here's the equation for K. Convective available potential energy. And what are we doing in that equation? We are comparing the rising parcel's temperature to the temperature of the environment. So, using this as an example, this is our rising parcel. And this is the environment. So we're comparing these temperatures as we work our way up in the integration process. And it's all based on parcel theory. But to whatever extent you want to believe parcel theory, you can calculate a maximum ascent rate. These are some ballpark numbers. I'm not going to ask you to recite those. But generally, the bigger the cape, the greater the likelihood of having some kind of severe weather. We had sin. Sin is just a way of quantifying a negative area. And to the extent that we believe in parcel theory, we can compute the maximum amount of ascent that is required to overcome the negative area. And when we talk about sin, frequently we're talking about a sounding that has some kind of inversion or cap that has to be overcome. And you remember the example that I used. You could have 10,000 joules per kilogram of cape, but if you have some sin and the atmosphere is not able to overcome it, nothing happens. But if the atmosphere is able to overcome sin, Then with 10,000 joules per kilogram, you wanna run for cover.
Now, those are just approximations. They really aren't that effective at quantifying that specific number, correct?
Yeah, they're only approximations, that's all they are. But, the main purpose here is to see that, well, if I plug into this equation, I get some values that are of the order of meters per second. And those are not synoptic scale values. So the bottom line of all of that was synoptic scale vertical motion typically is not going to be strong enough to overcome the sin. You're gonna have some kind of mesoscale forcing superimposed on it. Whether it's an outflow boundary, a sea breeze front, whatever. Because mesoscale vertical motions, they are of the order of meters per second.
Centimeters per second.
Hmm?
Centimeters per second.
Not in the case of mesoscale.
Oh.
Mesoscale is meters per second. Synoptic scale is centimeters per second. But when we calculate it, what we're gonna need is meters per second, and synoptic scale motions are not able to give that to us.
We're not responsible for the actual values.
No,
Okay.
no. About the only value that we've talked about is a dry adiabatic lapse rate. So, you know, at this stage of the game, everybody needs to know what the dry adiabatic lapse rate is. I'm not big on asking numbers. I'm more interested in concepts. And I'm sure I've said this several times, but I take the approach that if you can explain something to me and I understand it, then that means you understand it. But if you can't explain it, then probably you don't understand it. Or if you explain it in the wrong way. So that's my line of thinking. Accelerating downdrafts, microbursts, air that is accelerating downward. Kate was talking about ascent. Downdraft Kate, which is abbreviated DCAPE, D as in dog, DCAPE is how much negative energy do I have? If a parcel starts down, probably in a thunderstorm, will it accelerate downward and maybe give you a microburst? DCAPE is on the SPC sounding site and probably most sounding sites. And you have what they call the downrush temperature. So if you're standing outside and a downburst or microburst occurs and doesn't blow you away, you can look at your watch if it has a temperature device on it and see what the temperature of that downdraft air, and it ought to be close to this downrush temperature. And it has to be colder than the environment temperature, doesn't it? Or either it wouldn't be sinking, it wouldn't be accelerating downward. Any questions about this? Speaking of D as in dog, Terry Dog, my little boy, he really likes the cooler weather. Because he has a double coat of thick fur, and hot weather and him just do not get along. So he has been extra sporty when we go for our walks. I'm not gonna ask you to list the assumptions in partial method. I just wanted you to know that, they're scary, but we work with partial theory nonetheless, so I'm not gonna ask you these. Mm-hmm.
So, I'm a little confused about what you mean by that. Do you just want us to know that partial method is a type of method that we could use?
It's a simplified way of talking about air that is rising or air that's sinking. We treat it as a balloon with solid sides, elastic sides, but it's totally isolated from the environment.
So you would want us to know like the shortcomings of partial method rather than everything that makes up partial method?
Well, the shortcomings are tied into all of these things, so no. Just know that it's a crude approximation, but we use it because it's easy. And the only other thing that you would need to know is that, hey, we're treating a parcel like it would be a balloon. But we don't see balloons floating around in the atmosphere, rising and sinking. But to start off this discussion of hydrostatic stability or instability, we are using partial theory. That's what CAPE was all about too. Then we got into the layer method. So there we're not talking about individual balloons, we're talking about layers. So it's a little better.
Is that kind of what you want us to be able to explain, is like why it's a little bit better?
Yeah, I don't know that I would ask that, but
Okay.
dealing with the layers makes more sense than dealing with a little balloon.
Yeah.
So that's about the extent of it. But the big take home about the layer method was some rules. And all of these rules here assume no saturation. So if you play with a piece of semi-log paper, you could prove all of these. I'm not going to give you a piece of semi-log paper and ask you to do it, but there are a few of these that are important. Like number 1, lifting causes an originally stable layer to become less stable. That's something we ought to know. The converse is true too. Inverse, whatever. Substance sinking causes a stable layer to become even more stable. These are the two biggies of the lot. If you want to express it in terms of convergence divergence, 1 and 2 correspond to 7 and 8. So those 4 you need to know. Just as a matter of practical experience. So a forecaster, say, is looking at a dry line and they see a meso low develop. Well, meso lows mean you should have rising air. Well, so what? Well, if you have instability, well, you can release the instability. But the rising air in and of itself makes you less stable. That's rule 1. So at the same time that you're becoming less stable due to lifting, you also get this trigger to set off whatever cape you have. So it's sort of a double whammy. So, rules 1, 2, 7, and 8 are not just of academic interest to us. People use them. Then we got into the world of, okay, we're not going to just say no saturation ever. We're going to allow saturation to occur. And that got us into the world of potential stability. Potential, yes.
So for the layer method, we just need to know those rules.
Yeah. Those rules, you know, are for unsaturated air, air that stays unsaturated. Now we're saying, okay, let's stay in the layer method, but let's let some of the layer become saturated. So we have two situations. We have a situation in which here's the surface. Moist air near the surface, dry air aloft. In a situation like that, how do we expect equivalent potential temperature to vary as you go up in the atmosphere? Do we expect it to become smaller as you go up, or do we expect it to become larger as you go up? Smaller. So, if theta E decreases with altitude, we are potentially unstable. This situation is almost always potentially unstable. If we have moist air on top of dry air, just the reverse. Then theta E is probably increasing with altitude, and we are potentially stable. Don't confuse potential instability with conditional instability.
Because one uses layer and one uses
Parcel.
parcel.
So, with the term conditional instability, all we're saying is that the lapse rate lies between the dry rate and the saturated rate. That's it. With potential instability, we're saying, I'm stable now, but I could become unstable if the layer is lifted enough. And how much is enough? If we take a layer and lift it until all of the layer, top and bottom and everything in between, becomes saturated, if we're potentially unstable, the ending lapse rate will exceed the saturated adiabatic rate. And so what? It has become unstable. But it had to be lifted first. It had to be lifted enough. It had to be lifted such that top, bottom, and everything in between reach saturation. But if theta E decreases with height in a layer, and if that layer is lifted such that the whole thing becomes saturated, we know without even doing it on a SQT that the ending lapse rate will exceed the saturated rate. If theta E decreases with height. Contemplate on that for a moment. Potential. It's not stable. It's not unstable to start with, but if I lift it enough, it could become unstable.
Can you lift it by either surface heating or mechanically?
You can lift it either way. Usually, probably lifting is gonna be the way. I won't say 100% in order to make the whole air saturated, but, hadn't really thought about that. But this, in theory, it should be either. Questions about this? This is important stuff. On the SPC sounding page, they have a vertical profile of theta E. We've looked at it. And we could tell whether theta E was increasing with height or decreasing with height. Potential instability. Big thing. And potential instability is not the same thing as conditional. So here we had our dry air on top of moist air. I went through this in class. We lift the whole thing. I end up with that lapse rate. And you can tell by the slope that that lapse rate exceeds the solid green line, which is the saturated bed. Dry air on top of moist. So we can prove it to ourselves on this QT. You can also prove it to yourselves mathematically. Here we have moist air on top of dry air. We lift the whole thing until it becomes saturated. Theta E is increasing with height here, and we end up with a lapse rate that does not exceed the saturated rate.
Are you gonna ask us to draw this with the example?
No. Let me ask you, in this case, how is it that dry air on top of moist air gives a lapse rate that exceeds the saturated adiabatic? How can that be if I lift the whole thing to saturation? It's not just magic. And you have all the tools to explain it. I'll try to explain it. I think I can. Dry air is going to cool longer at the dry adiabatic lapse rate before it finally becomes saturated. The moist air at the bottom is not going to have to cool as long at the dry rate before it becomes saturated. And of course, the saturated rate is smaller than the dry rate. So, what part got cooled the most? The top part that was dry or the bottom part that was moist? Which one ended up having the most cooling after the whole thing was lifted? Top or bottom? Top or bottom? Bottom or top? Which one cooled the most during that process?
The
Top.
The top.
And you have cool
So-
air on top of warm air.
If we take a lapse rate, just any old lapse rate, it's going to be the pencil lapse rate, and the top cools more than the bottom, what's that gonna do to the orientation of the lapse rate? It's gonna bend it over. Y'all see that? Anybody have any questions about that?
Can you go with that again?
Yeah, we're gonna lift the top and the bottom. You know, we define our layer, top and bottom. The top is dry and the bottom is moist. And we lift the whole thing. Top and bottom and everything in between. The top, because it's drier, is gonna cool longer at the 9.8 degree rate than will the bottom, that will only cool at the 9.8 degree rate for a short vertical distance, comparatively short vertical distance. And then both of them cool at the moist rate, which is smaller. So the top cooling longer at the dry rate ends up having cooled more than the bottom, which cooled at the dry rate for a short distance. And then cooled at the saturated rate.
And so you're supposed to keep the same pressure difference as well, right? So that you can assess it.
Yeah, the same pressure difference, but it won't be the same geometric height difference, but the same pressure difference. So we lift the top and the bottom each, say, 500 millibars. Whatever it takes to get it, the whole thing saturated. And one of the great things about theta E is that by looking at how theta E varies with height, we know ahead of time what the end result of the lifting process would be. It guarantees us that if theta E decreases with height, the ending lapse rate will exceed the saturated rate. And you can prove it. You can prove it on SQT, you can prove it mathematically. But we don't have to use a SQT to ask ourselves, will this succeed? If we know theta E top and bottom, it's guaranteed to give us the right answer. That is one of the nice things about equivalent potential temperature. Questions about that? Mm-hmm.
So if the lapse rate is like greater than the moist adiabatic lapse rate, then wouldn't the air sink?
No. We're talking about lapse rate. We're not talking about a parcel now. We're talking about lapse rate. And we're saying if, is the lapse rate greater than dry adiabatic, less than dry adiabatic, greater than saturated adiabatic, less than? So we're talking about lapse rate. I believe you're thinking parcel.
But if the lapse rate is greater, doesn't that mean it cools more? And if it's colder, then wouldn't it sink?
It all depends on how the parcel's temperature compares to the temperature of the outside environment. So in order for something to sink, the temperature has to be colder than the surroundings. So it's not a matter of just what is its temperature. It has to be colder than the surroundings in order to sink. And likewise, for something to rise and accelerate rising, the parcel has to be warmer than the surroundings for it to be buoyant. We just briefly mentioned these other indices. There's a ton of other indices, but these two are the most commonly used of the others. And the thing they all have in common is that there is no integration involved as we do in K and sin. We're only looking at individual levels. And it's always better to look over a layer than at individual levels. That doesn't mean there isn't any use in them. They're on the SPC soundings. The K-index is especially useful during the warm season because it seems to be pretty well related to what used to be called air mass storms. These pop-up, supposedly random storms, but they're not truly random. So, just know that these things exist. So, here was LI, so forth. Getting back to parcel theory, we have the Leff's rate change equation. And here's the change of Leff's rate with respect to time. We have a diabatic term, a horizontal infection term, this funny term that we said was small, a divergence term, and a vertical infection. So once again, do not memorize equations. But if I give you the equation, you need to know what it is. Any other questions about that section on hydrostatic stability? Yes, sir.
Would you want us to know the terms of the lapse rate change equation, like the names of them?
At least to some extent, you wouldn't have to give the precise term, but be able to, well, this term looks like an infection term, or this looks like a diabetic heating term, or something like that. We didn't go into them much, so it's not a big thing. And once you think about it, it all makes sense. It's just that now we have an equation. So probably the answer is no. Mm-hmm.
Did you want us to know, like, the lifted index and, like, those numbers and the K index?
Absolutely not. I do not ask numbers.
And then, would you want us to know, like, what they are?
Well, you need to know what the lifted index is. You need to, and what is it? Well, you're lifting a parcel up to 500. Okay? Well, that's sort of like K, but here we're stopping at 500, period. And all we're doing is comparing the two temperatures, parcel and environment. Whereas with Cape, we were vertically integrating all the way up. And K index, it's an empirical equation. So people, somebody, some group sat down way back yonder and decided, well, these three things seem to be a big help in forecasting summertime storms that are somewhat random in nature. Anybody else? Photographs. We're gonna hand back the photograph lab. If you can do everything that was asked on the photograph lab, then you've got it made. There's a photograph. So we went through all of this stuff, and you did it on the lab. So you did storm relative motion, ground relative motion, horizontal vorticity, storm relative vorticity. All that stuff you did, but if you don't know what those terms are, you know, we talked about what is storm relative motion. Well, you need to be able to describe it. What is horizontal vorticity? How is it different from what you spend time in dynamics class talking about? In dynamics class, you probably spend all of your vorticity time talking about the vertical component of vorticity. But horizontal vorticity is about a horizontal axis. It has a direction, it has a magnitude, it's a horizontal vector.
In the lab, there was one case where when you were trying to do the horizontal vorticity, the streamwise, the streamwise vorticity and the crosswise vorticity, it was so close together. When you?
I'm not gonna give you one of those,
Okay.
if I give you one. I'm gonna give you one where it's lots easier to tell.
Like the second one, that was much.
Yeah.
Okay.
Would you give us something kind of like the extra credit where you're like, oh, show, or like draw or sketch a photograph that would have, that would be favorable conditions for?
Probably not. That was something Jonathan dreamed up. It was an interesting exercise, and hopefully you did it and got it right. But, I'm not gonna ask that.
So basically you're saying, with all this, just know the terms on top of how to find them on a photograph.
Be able to describe the term in words.
Yeah.
And be able to do it on a photograph. Like you did in the lab. I didn't ask you to define each of them in words, but now I could, as well as ask you to do it. So, we use the word unidirectional shear. A photograph that we would call unidirectional, or at least a deep layer of it. Unidirectional, what does it mean? Well, it means that the shear vectors have the same direction. It doesn't mean that the winds have the same direction. It means that the shear vectors do. Some things got mixed up a little bit here. Now, any photograph that I would give you, if I give you one, it's not gonna be curved the way some of these pictures were. It's gonna be straight line segments because they're easier to work with. And that's what most people use. Yeah, this is my second effort at trying to explain this because I didn't think the first one went well. So, we started off here with three-dimensional vorticity, went through the cross product stuff, looked at the horizontal, so I component, J component, compared magnitudes, and we found that horizontal vorticity is directly related to vertical wind shear. That's why we're interested in vertical wind shear anyhow. We're interested in vertical wind shear because it is so closely related to horizontal vorticity. Why are we interested in horizontal vorticity? Because if a storm develops and it has an updraft, it can tilt it up and you can have a rotating updraft. That's why. Any questions about that part? So, as is the case with virtually everything we do in here, it's not that horizontal vorticity is of strictly academic interest to us. Horizontal vorticity is important to us, vertical wind shear is important to us, because it is the factor, the vertical wind shear is the factor that is going to determine whether you have a cyclonically or anticyclonically rotating updraft. And why are we interested in that? Because that could give us a tornado. And people don't like to be blown away by a tornado. Now, we in the lab, we had a horizontal vorticity vector, and we broke it up into two components, streamwise and crosswise. So you want to make sure that you know how to do that. So if you copy somebody else's lab and don't know how to do it, you need to go back and figure it out. So any questions about all that good stuff? This is all good stuff. It really is. It's what separates the educated meteorologist from the uneducated meteorologist. Thickness. Thickness is the geometric distance between two pressure levels. And you pick the pressure levels. The most common ones are 1,000 to 500. But you don't have to. The thickness in a layer is proportional to the mean versus temperature. Well, so what? That means that we can use a contour analysis of thickness to help us find fronts. So we had a couple of examples here. Here's 1,000 to 500 millibore thickness. And, you know, we went through this little exercise here to say where the thickness lines first start to become packed. Where the gradient first starts to increase, that is probably where the front is. Does this take the place of all the rules we learned earlier in the Finding the Front page? No, it's an extra rule that hopefully will help us even more. And why do we put it at the leading edge? The front at the leading edge of the thickness gradient? This diagram tells us. We had some rules that pertain to thickness that tell us how pressure systems vary with altitude. And those that I have the red circles by are ones that you need to be able to prove. And we proved several of them in class. One set of rules says, okay, you know, the warmest air or the coldest air is sitting in the middle of my high or low, whichever the case may be. And then we had a couple of other rules that say, well, what if the cold air is displaced to the west, or the warm air is displaced to the west or east, or what then? And we went through some examples. First thing you gotta do is to draw a pressure surface, draw a couple of isotherms that indicate whether it's cold core or warm core, and then deal with the thickness and work your way up. I think I promised you one of these. I'm not gonna break my promise.
So when you ask us to prove it, you're looking for, these diagrams, correct?
I'm asking you to make the diagram and to explain how it shows whatever the rule is asking you to show. So a diagram by itself is not enough, even if it would be correct.
But you verbalizing, oh, for a warm core cyclone, for instance, you see that it's converts to a anticyclone by, and just describe what the diagram looks like, then that's.
Well, the key phrase in this, in practically all of these, is gonna be, wherever the cooler air is, I'm gonna have smaller thicknesses. A smaller separation between two pressure surfaces. Wherever the warmer air is, I'm gonna have a bigger thickness between the two pressure surfaces. That's what it all boils down to. And if a person wouldn't say those words, then, you know, your diagrams don't indicate what's going on. Even though pictorially they might, but you gotta say the right words.
Would we need to know like what each rule is in words, or would it be like you give us the rule, we describe why?
I would give you the rule. Although, I think it would be fair to say, how does a cold core low tilt with hot? And you would say, well, it tilts toward the cold air with hot. I think that would be fair, but it would probably be more straightforward for me to give you the rule. And I guess similarly, how does the strength of a warm core cyclone vary with hot? And you think, hurricane. Well, its strength is going to become weaker with hot, and it'll turn into an anticyclone a lot. So, once again, we see these things. And Eric Bunker Wednesday, he was talking about the tilt of this humongous, mid-latitude cyclone that pounded Europe, or western parts of Europe. Would you find baroclinic and barotropic? I guess I'll let Dr. Wayne go with that. Thermal wind. It doesn't blow. It's a vertical shear. And not just any old vertical shear, but the vertical shear of 2G strophic winds. So we came up with a few important conclusions about this. Wherever thickness lines are packed, have a big gradient, That would be a highly baroclinic region, to use more sophisticated language. And in that region where the thickness lines are packed, we'll have a lot of vertical wind shear. In regions where we don't have a lot of packing, we won't have a lot of vertical wind shear. The winds won't vary that much with height. I'm not gonna ask you this. That's not to say you shouldn't know it. But if the geostrophic winds veer with height, then you have warmer advection. If they back with height, you have colder advection. I'm not gonna ask you that, you've had that before, but that doesn't mean that you should forget it.
Does vacuum and veering have the same definition regardless of hemisphere?
No.
I don't know. He says no, I'll take his word for it. I don't think about it, that's for other folks. But I'll take your word for it.
That's Alquist's word.
Questions so far? We got one more section. Our last section. And this last section, for the most part, has to do with cyclogenesis. Chapter 5. Why do we have Atlantic cyclones? Well, energy balance, and the atmosphere is important, and all that good stuff. And we have a map that we wanted to explain. You certainly need to know this diagram. Because we make use of these concepts in upcoming pages. The first topic on the cyclogenesis agenda was, how come is it that cyclogenesis is favored when a trough aloft approaches a surface stationary front? It's an old saying that's true. And we were able to explain it using the vorticity equation. So, I think you know the names of all these terms. You can tell just by looking at them what the names should be. This is an advection, a horizontal advection. We have omega. Ah, okay, this is a vertical advection. Here we have how omega varies in x and y. That has to be a tilting term. This is a divergence term, once we substitute. Right now it's partial omega squared p, and we have friction. So we can look at an equation like that. And by now you know the form of terms. Horizontal advection, vertical advection, divergence, what have you. So to prove our statement about cyclogenesis along the surface stationary front, we use that equation. Specifically, we looked at that term. And we had an example here of a shortwave trough approaching a frontal boundary. And what's the big difference between what's happening in the frontal boundary versus what's happening outside. What's different about the green area than the white area? It's the vorticity. Here, winds, more anticyclonic, whoa.
I think you're spinning a little wrong.
I'm spinning the wrong way. But we have cyclonic vorticity. Fronts are in the trough and yeah. It's Friday afternoon. That's why we don't have exams on Fridays.
Amen.
I don't know if you're at your best on Friday afternoons. I'm not. So we let the convergence be the same, green area or white area. But what's really different is that we have more cyclonic vorticity in the front region. So this term here, and you say to yourself, I don't see horizontal convergence, divergence in this term. Well, where did it go? Here. We make a substitution for this, and voila, we have horizontal divergence. But we have a preceding negative sign that comes into play. So, yes, when an upper, and we haven't really mentioned the upper level trough, because that's going to do its thing wherever you are. Whether you're in the frontal zone or outside the frontal zone, you're going to have PVA ahead of it. But what's different is that when it passes over here, now we get some upper level support from that trough superimposed with the enhanced vorticity of the surface. Somebody had a question.
So at the very beginning, it's the flow coming from the two highs that starts to spin up, and then the trough will assist later on with the approaches.
Well, you know, the front sits in a trough because there's high pressure north, low pressure in the other direction. So fronts, you know, have to be in troughs because they separate air masses. But because it's in a trough, we have more cyclonic vorticity. Yeah.
But do the flow of the ridges also help out?
Flow over ridges, well, are you talking about mountainous type ridges?
No, like the
Or
two
high pressure ridges?
systems, like what you do with the pencil earlier.
You're talking about the two flows of this high pressure systems with the.
Well, that gets back to what we were saying, is that, okay, the front is in a trough. If it's in a trough, there has to be high pressure on one side, high pressure on the other side. And in between the two, there has to be comparatively low pressure. I'm not sure we're on the same page.
I think we're talking about the same thing indirectly. I think I understand now.
Okay.
So just to clarify, those high pressures are associated with the 500 millibar trough, and that's what's moving into the frontal zone. And
No,
They're surface.
the H's would be surface H's.
So then what is the role of the trough?
The trough gives it some upper level support. But, you know, the trough can move along whether there's a frontal zone or not, and probably nothing happens. But if it passes over this surface stationary front, well, there we have not just the upper level support by the trough, but we're getting some support at the low levels too. Is that kind of tied together? Here were our conclusions. I guess the conclusion, say all this stuff in a nutshell, is that really we've been only thinking about two terms, and we really only focused in on one. We haven't talked about vertical eviction, we hadn't talked about tilting, we hadn't talked about friction, we hadn't talked about any of that. And the reason we hadn't talked about any of that is because usually they're not the important things leading to cyclogenesis. Now, in meteorology, you will learn, I've already learned, you don't ever say never. As soon as you say never, it's gonna happen. Then we had a little playback. Here was our mass continuity equation. If we're gonna have falling pressures, we gotta be losing mass. But we didn't approach it from that point of view, even though it's true, because del dot rho v and del dot v are difficult to compute accurately. They're easy to compute, but difficult to compute accurately. So we go in the back door with the vorticity approach. Okay, we have a baby lobe. And it probably formed on a surface stationary front. And this trough back here is probably what caused it to happen, along with the fact that surface stationary front had enhanced vorticity. So now things are getting going. And so the question is, what happens to the trough aloft and to the downstream ridge? They've done their thing, they have gotten the cyclone started, but now what? And that's what typically is called self-development. Self-development is, okay, now they're gonna feed on each other. The upper level and the lower level are gonna feed on each other in a positive feedback. And so we had a different equation that made things easier for us to figure that out. And the T in bracket, you remember, was mean virtual temperature in a layer. Local time tendency of layer averaged, should have virtual in here, but layer average temperature. Got some terms. Horizontal advection. Here we have a vertical motion term, we have a diabatic term. So this is a term, it's an approximation that enables us to tackle this idea of what happens aloft. That's what we're asking ourselves. Does a cyclone become a bomb or whatever it's going to be, really develop, and the trough and ridge don't do anything? They keep their intensity that they had to start with. No, they don't. The trough ridge is going to intensify as the surface low intensifies. And the big term here is this one. The advection of mean temperature. Here's our baby cyclone. Warm air advection here, cold air advection here. If I have warm advection, that's going to increase the thicknesses. If I have cold air advection, it's going to decrease the thicknesses. So that means that this trough is gonna get deeper and the ridge is gonna get stronger. Yes?
I know you mentioned earlier that you wouldn't ask us a question about a warmer advection and colder advection regarding like thermal wind and stuff like that. But would you give us something like this and ask us, okay, on which side of the low is
Sure.
the warmer advection and cold advection?
Absolutely. Everybody should know that. If a person thinks that cold air advection is occurring here, you're in bad shape. Or maybe, you say over here behind the cold front you have warm advection. Cold front comes by and it gets hotter. No, I don't think so. So, this term is what we focus on. And it's gonna change, like I just said. The trough is gonna become deeper and the ridge is gonna become stronger. So as the cyclone at the surface intensifies, the wave aloft becomes more amplified. So, they're not two separate worlds. What's happening at the surface with the cyclogenesis bears on what's happening, say, at 500 millibars. These are 500 millibars. They're not totally separate. The atmosphere is three-dimensional. Everybody understand that?
Just conceptually, the cyclogenesis is just for getting genesis to occur, and then once that's done, then we can use the seventh equation to explain the amplification.
And what we've done here, we've picked equations that make it easiest for us to decipher what's going on. We could come up with some basic primitive equations and go through all this and have one equation, say, for everything. But it'd be hard to figure out. So we picked the vorticity equation because it was the easiest way, and one term in there particularly, was the easiest way for us to understand what's going on to start the cyclogenesis process. It was not a good equation for understanding what's happening at 500 millibars though. So now we approach 500 millibars from a different perspective. And thickness, you know, top and bottom, the bottom can be the surface where the cyclogenesis is occurring. And so now, surface to say 500 millibars, what's going on in that layer? And we can then infer what's happening at 500 millibars. So we pick an equation, as long as it's a valid equation. We can't pick, you know, something goofy, but we pick an equation that best tells us what we're trying to figure out. And so, in this case, there were two different equations. So, this would be a cross-section of view of it. Now, you can think to yourself, or maybe your mind doesn't work this way, what if it gets out of hand? And that's sort of what happened this week with that cyclone on the way to Europe. Things got kind of out of hand. That low really became deep. We saw it. We read about it. But thankfully, it's probably not going to get any deeper. In fact, probably it's already as deep as it's going to get, and it's starting to decay. What keeps cyclones from just going bonkers? This term. And if we assume that we're not super adiabatic, either moist or dry, whatever the case may be, then the vertical motion is going to determine the sign of this term. Let's draw a picture.
Would you have us recite those different terms from this?
Sure. This is an important equation. We're explaining what happens at 500 millibars and what keeps it from becoming a disaster. So if I give you the equation, then you need to, and you would say, okay, this is the horizontal advection of mean temperature, and that's what we're looking at, say, to get at 500 millibars, and this is our breaking term. So remember that term, breaking? So this term tends to counteract this term. So let's look at that. In this region over here, do we expect rising air or sinking air?
Rising.
Rising. So that means omega is negative. And back here, after the cold front passes, do we expect rising air or sinking air? Sinking air. So omega is positive. And since we've assumed we're not getting super adiabatic, the term in parentheses is always positive. So it all depends on what the sign of omega is. So in the area east of the low, omega is negative. Partial of mean temperature respect to time, that term gives us a negative contribution there. But we just got through saying that this is where warm air advection occurs. So this term is positive here, and this term is negative here. But until the vertical motions get too strong, the advection term wins. But if the vertical motion gets too strong, then the brake gets pounded.
Can you repeat that last part where you just said?
Well, we're saying, okay, well, you know, the ridge gets to be stronger and the trough gets to be deeper. Can that keep on going without limit? And we said, no, it can't, because the sign of this braking term is going to be opposite that of the advection term. I don't think that's exactly what I said before, but it's close. We never want to forget our diabatic term. Q dot. If we have latent heat being released, I always use that as an example. Like our bomb did all the damage the other day in Europe. That helps to strengthen the trough a lot. And all of this is in a positive feedback. I didn't stress that too much, but it is. That's that word self-development. And y'all laughed when I said I thought it was sort of incestuous. But once you get the cyclonic circulation and the warm air advection and the cold air advection, that tends to feed on itself. it makes the ridge stronger, it makes the trough deeper, and now we have more support in the upper levels to further deepen the cyclone at the surface. So we get in a loop. Breaking term. And this in words is what I just said. And that's it.
Amen.
We're not gonna, well, one other thing,
No.
we had to talk about lee side cyclogenesis, but that's a potential vorticity thing, and I'll let Dr. Wing handle that, and y'all will have plenty of that until, well, next semester, and you will get a belly full of it, so. And this version we won't go into, it's just a more elaborate version of what we are. So Monday is lab day.
Do you want us to know about voucher layer turbulence?
Oh, yeah, bombs. Bombs, thank you. Yeah, you need to know that. I'm looking at the clock and getting tired, and yeah, bombs. What's the big distinguishing factor between bombogenesis and cyclogenesis? It appears to be the turbulent transport of heat and moisture from the water. Not that you couldn't have it over land, but you wouldn't have as much of it. And it wouldn't be as much of a tipping point. You get your bombogenesis or not.
I feel like this one has so much. There's so much material.
So, yeah,
Put that also
this
needs to be-
page here. I thank you for reminding me of that.
Optimistic way of looking at it.
Run, dude. Now we're at the. So, y'all have a good weekend. We'll see you Monday.
Yeah.